the homework on the supremum. If you attempted it, you may have noticed that one of the problems was not phrased in a way that it was actually a statement. It was an imperative in which I said you should let something happen. But then there was nothing, there was no statement after that before. So there was nothing to do. I have updated the document online. Unfortunately, that doesn't update your paper copies. I don't know how to do that. With the actual statement. You're supposed to classify the set of all upper bounds. The set of all upper bounds is the set that starts at the supremum and goes on forever at the interval from S to infinity. That problem is now not a homework problem, as advertised in red. Cool. There's one announcement. The other announcement is like logistics. Well, it's not directly related to any class content. So for that email that you all got, and I think, well, I got it, probably you all got, the mask mandate is being lifted as of the week before spring break or something. Cool. So, if you read my syllabus language says that I want to require masks regardless of university policy. I have been told that I cannot enforce such a requirement. So, I'll ask that you all keep wearing masks, but if you don't, there's literally not going to be any negative consequence in terms of like class stuff. That being said, I've been cautioned that, you know what sounds like it will probably happen when the masks go away?
Can you shoot back up?
Well, sure, COVID, but also just the flu. Get your flu shots. All right, cool. So, here's the order we're going to do things. We're going to finish up the stuff in that notes, then we're going to do one more thing, and then we'll start up a new topic. Here's the last thing in the notes, the density of the set of rational numbers. Theorem. For any real number x, I was pointing at the sheet. For any real numbers, x less than 1, there is a rational number q, which sits between x and y. There's the thing we want to prove. Let's prove it. So let's think about what we want to show. A rational number has a form p over q. Maybe it'll be m over n, because q has a form. And then m over n can be, I don't care what rational number there, it just has to be something in between. So that means I would be just as happy. I would be happy with that. It's a rational number, the denominator should be positive. Oh, cool. If I move, so if I want to multiply x and y by a really big number, can I make the difference between x and y really big? Yeah, and like more formally, for any difference you want x and y to be, there is just a natural number of x such that n times x minus y is that big. We proved that in our last thing. That was one of the results. Well, neat. That means I can get these two to be bigger than 1 in difference. If I have any gap of size 1, we've proven that you can find an integral between them. Oh, so then you get this? Without it, get that. So now let's put that into y. Proof that x and y be real numbers. Assume that x less than y. That means that n times x minus y is bigger than 0. So take a look at theorem 2.5.5. With A being x minus y and B being 1, to make a conclusion. There exists a natural number n such that what happens? So if you like, take a look back at theorem 2.5.5, tell me what you can do. What does 2.5.5 say?
You know that for all n in the natural numbers, n is less than or equal to b times a inverse.
Adjust those quantifiers. That seems not quite right. We know that if A and B are any real numbers and A is bigger than 0, then there exists a natural number, not for every. Cool. Given the things stated on that other page, is that number A that I picked bigger than 0? And and b is 1. So I can find a natural number n such that x times y, x minus y times n is bigger than 1. That's all. Y minus x, because that's the thing that's actually positive. So let's suppose I ask you to take that and solve it for n times y. What can you tell me about n times y? What is it going to be bigger than? Do the actual simplification on paper if you need. There's going to be like some distribution, and then you'll add something to the other side. Yeah. Cool. So what do we have right now? We have Gesundheit. There's ny. Nope, there's ny. Is bigger than nx plus 1. There's nx. Now, appeal to lemma 2.5.7 with z equal to nx. What does lemma 2.5.7 allow you to conclude? And I don't expect you to have memorized what 2.5.7 means, but you have the notes in front of you.
For any z in the real numbers, there is an integer in z, or the range of z to z plus 1?
Yeah. So, for any z, so this z in particular, there's some integer m with m in the interval from z to z plus 1, and one of those was inclusive and the other one was exclusive, right? Which way was it?
Exclusive on the z side, inclusive on the z plus 1 side.
Awesome. Explain how to show that nx is less than m is less than ny. Well, let's just write down the things we know. So maybe we'll start here. As m is in z to z plus 1. And in fact, that z is an artificial. There's no need to introduce a new variable here, nx. We get a conclusion. Nx plus 1. I know that nx is less than m is less than nx plus 1. And I need m to be between nx and ny. Do I already have m bigger than nx? Yeah, it's like, that's this line. Oh, yeah.
You said you wanted m bigger than n or n bigger than n?
I want this.
Oh.
And maybe I'll shift down so you can see. So I already have one of the two things. We already have nx less than m. Now we just need m to be less than ny. Let's see, what do I... Oh, this should be less than or equal to. What's something that I know is slightly bigger than m? Or at least as big as m? Well, there's something. So let's see, since m is less than or equal to nx plus 1, and I eventually want m to be less than ny. But what do I know about nx plus 1 and ny? I know this, right? So since m is less than or equal to nx plus 1 is less than ny, m is less than ny. So nx less than m less than ny. This parameter n was a natural number, so it's positive. Well, you all have proven that you can divide an inequality by a positive number, and it resolves the inequality. So, we can divide by n to get the inequality x less than m over n less than y. Have we now found a rational number strictly between x and y? So what? Cool. So before I start in on the next thing that I want to talk about, well, maybe I should ask, do people have any questions about how that proof went? Yeah.
What does it say, under the limit thing,
Oh, yeah, that's totally illegible. As m is in the thing that you know m is in. So let's see, that's nx to nx plus 1. So the same thing is here. Yeah. Neato. So, I think the next thing I want to do is have a pop quiz, which is probably not so surprising this time, because I told you what would happen and I just forgot to do it last time. So, I'm going to distribute some pieces of paper. Take a piece, pass it back one. That's probably one plus of it. No worries. And you know what I'm about to ask, so go ahead and start answering if you want. But here's what I want you to do. For any set x, s is the supremum of x means yeah, I maybe object to some of the informalities on it. Okay. And probably hard to stick like that.
Sweet. Fortunately, I'm still working on the formality of language.
Yeah, that's one of the points of the class.
Yeah. Physics background.
Do I have it where it's at? Oh, okay. All right. I'm definitely much happier than when I asked on Monday. So, I'm going to write down, so let's write down the definition. What does it mean to be the supremum? Yeah.
that your supremum is greater than or equal to all of the x values in set x?
And some language that I would maybe object to here. Like that's maybe a little bit too involved. As bigger than it would be for every x and x. It makes it a little bit stable. So that's half of it. That's what it means to be an upper bound. What else do you need? Yeah.
S is greater than or equal to u for u is any other upper bound of x.
And I'm never really sure what proposition goes there. Is it an upper bound for a set, is it an upper bound of a set, an upper bound on a set? An upper set, yeah.
Isn't S supposed to be less than or equal?
Oh, yeah. Least upper bound, not biggest upper bound. There is no biggest upper bound. You said less than, right?
I don't remember.
Probably did. Nice. People feel like they wrote down something that was reasonably close to that? So there was one other option for the second one. We have another condition that's like equivalent to that, right? This thing that involved epsilons. So another thing you could have written so those were the two reasonable things you could have written down. I guess maybe since I said means, that's hinting that I want the definition non-equivalent statement. So this is probably the better answer to the question as given. Let's see. So the ones which were written down which I didn't like. So there's at least one submission that was missing the following epsilon bigger than 0. And that's important, right? If you don't specify whatsoever, then the reader doesn't know what epsilon is, whether it's a particular number, whether it's every number, whether it's even a number. The reader would have to infer that based on the fact that there's an inequality. So that's important. And this quantification for every epsilon bigger than 0, there is some x with this happening. Like it's very precise language that means exactly what it's supposed to mean. Cool. We'll see if I ask this again on Monday. I'm pretty happy with the result. People feel pretty okay? All right. So I want to start in on something new. The something new is shifting gears to something which will seem much more familiar because it's something that you studied in calculus. In calculus, well, let's see, in any of the calculus classes, was this notion of supremum mentioned? I don't think it gets mentioned in the standard calculus curriculum. It's very important. It underlies basically everything that we do. But something you definitely did in calculus is you talked about sequences and their limits. So let's think about that. Does anyone not have that thing of notes yet? Cool. So this is what we're going to start in on. So what is a sequence? So in like Calc 1, you think of a sequence as being like an ordered list of numbers. Like you have a bunch of them, but you know which one comes first, which one comes second, which one comes third. Well, if you parcel that out a little bit, that just means for every natural number n, a sequence is a rule that associates to that natural number a real number. Well, that's a function. A sequence is a function from the natural numbers to the real numbers. The function from n to r is called a sequence. Often I'll write a sub n in place of f of n. And there will be a few notations we'll use. Sometimes I'll indicate my sequence and decorate with parentheses. I'll try to do that most often. Sometimes I'll write the sequence with parentheses, and then I'll advertise what its valid inputs are. Because like, sometimes you want a sequence to start at 0. Sometimes you want it to start at like 2. So I'll specify the domain by using some sort of language like this. Sometimes I'll use set voices to indicate a sequence. The book does. I don't like that notation because set voices should indicate a set, and the set doesn't know what its first element is. Right? Like the set 2, 1, 3 is the same as the set 1, 2, 3, but those are different if you think of them as sequences. So there's a definition. What do you do with sequences? So in calculus, you took limits of sequences. And let's just try to remember what that even means. So there are lots of different ways of writing it. For a sequence, xn, well, I said I didn't like that notation, and I'm using it immediately. And a number L, we say that the limit of xn is equal to L and a half dozen other things. If something happens, what should this mean? The limit of a sequence xn is equal to L. What should that mean? And I'm happy with anything formal or informal right now. Yeah.
As n increases to infinity, the value of x sub n gets closer to L.
I like that. Informal. As n goes to infinity. You said something about getting larger, but that's kind of captured in that. X sub n gets close to L. So I think the only thing that you need for more detail there is explaining what you mean by as n goes to infinity and what it means for x n to get close to L. And maybe we'll parcel it out this way. So that's what I mean for like, if you want xn to get close to L, it suffices to have n be big. So, for every proximity you want xn to be within of L, there exists some threshold so that after little n passes that threshold, xn is that close to L? And that's like sounding way more formal and complicated, but now like we have some quantifiers. Let's write that down. For every, and this is like a weird thing to say, proximity, you want xn to be to L. Right, so how close do you want xn to be to L? No matter how close you want that, there is some threshold so that once n passes that threshold, x sub n is that close to L. And that looks like complicated language, but it all sounds a little bit more informal now. It sounds more like something you can understand. Let's parse that out a little bit further. For every proximity you want xn to be to L, what type of object is that? Like a proximity should be like a distance? Yeah.
Like an epsilon?
An epsilon. If for every epsilon bigger than 0, that epsilon is the proximity you want xn to be to L. There's some threshold number. There's some threshold so that once n passes that threshold. What sort of thing is that threshold that n is passing? Yeah.
Delta?
I don't want to call it delta. Think about what type of object it is. You're thinking about like limits of functions of continuity. Remember that definition. So this little n is like getting big. Delta is like a small thing usually. That's why I don't want to use delta. So once little n passes some big number, let's just call that number a name. I'll call it big N because it's big and it has to do with n. For every epsilon bigger than 0, there is some threshold value, big N, so that if little n is bigger than big N, then xn is that close to L. So the distance from xn to L is less than epsilon. Well, distance is just code word for absolute value of the difference. There is the definition of what it means for a sequence to converge to a number L. So now that it's like written down, does that remind you somehow of like something that felt very complicated when you saw it in Calc 2? Hopefully that doesn't look so complicated by comparison to other stuff we've done. Like it's only as technical language, but it's now hopefully less unfamiliar. Let's use that definition. Let's prove some things. So if I give you a sequence, ask you to prove that that sequence converges to L, you need to show that no matter how close xn is to L, so for every epsilon bigger than 0, there is some threshold value, some big N. So you need to come up with a choice of big N. Then you get to assume little n is bigger than that choice of big N, which you got to choose. You got to say what big N is. Then you need to prove this. So let's do some stuff with that. And I think maybe we'll even skip that, go right to an example, and then fill in the stuff above. All right, so let's let xn be 1 over n. Where am I? There. Let's let xn be 1 over n. What's the limit of that sequence? What do you think it is? Use your Calc 2 intuition. Yeah.
0.
0, right? As little n gets big, 1 over big N should, 1 over n should get close to 0. Let us prove. So, xn converging to 0. Let's write down what we want to show. That means we need to show for every epsilon bigger than 0, there exists a trace of big N such that for all little n bigger than big N, x sub n minus 0 is less than epsilon. So, here's what we need to prove. So let's say the first thing we need to do is consider absolutely any epsilon bigger than 0. We do not get to choose this epsilon. Someone has chosen it for us, and it is very small. So the first line of the proof. Consider any epsilon bigger than 0. Now we get to choose a choice of big N, and I have no idea how big that big N should be yet. So I'll try to make an approach that is going to attempt to be like a halfway point between a first draft and a final draft. It'll be the final thing that I'll write. So I'll say, let's let big N be blank. I don't know what big N is yet. I'll figure it out once I have the proof written. Next, I have to consider any little n bigger than big N. So I'll suppose that little n is bigger than big N. And then I need to show that the absolute value of xn minus 0 is less than epsilon. And maybe we'll do some scratch work here. So tell me about xn minus 0. My end goal is that is less than epsilon. But what is xn minus 0 equal to? Yeah.
Okay.
Yep, that's equal to xn. Keep on going. Do stuff with that. Yeah.
That's also equal then to 1 over n.
Yeah. And like you didn't say absolute value, so maybe I won't write it. Should there be absolute value around that?
Yeah.
Okay. Do the absolute values matter there? No, why not? Yeah. N is positive. So 1 over n is positive. You've proven that. Okay, cool. That's equal to 1 over n. My end goal is this is less than epsilon. Now that we have the little n showing up, let's use the fact that we know little n is bigger than big N. Yeah.
How do we know that n is positive?
Because it's a natural number.
Oh, all right.
Yeah. All right. So a thing that we know is little n is bigger than big N. And I eventually want this thing to be less than stuff. So if little n is bigger than big N, what can you tell me about 1 over little n? Yeah. bigger than 1 over big N?
That's not what you said, but that's what you meant, right? You said greater than, you said less than.
Yeah.
Yeah. No, you're good. You're good. Nice. And we get to choose big N. Is there some big N that you could choose that would maybe result in those two things being equal? You saw this equals that and we're asked to solve for big N. What would you say? Yeah. Yeah, 1 over epsilon will do. Oh, nice. So now we have our choice of big N, and in fact, we have our proof written down informally to the side. So, choose N. It looks like big N, we'll take that to be 1 over epsilon. I'll assume that little n is bigger than big N. Then, absolute value of xn minus 0, well, you told me that I'll just follow your same steps. It's the same as absolute value of xn. I think this is enough space. Is equal to the absolute value of 1 over n equals 1 over n. Maybe here I'll use since n is in n, so little n is bigger than 0. I know that that's less than 1 over big N since little n is bigger than big N. Let's see, maybe that also needs big N to be bigger than 0. Like the theorem where we saw that involving flips inequalities, that was an assumption. Is there a trace of big N bigger than 0? Yeah, awesome. And what is 1 over big N equal to? Yeah.
N? No.
What is this equal to by our trace of big N?
Oh, epsilon.
Yeah. Right, that's why we chose it. Right, you could do it again. You could say, oh, that's 1 over epsilon. But you already know that that's epsilon. That's why you chose the damn thing. By our choice of big N. And maybe a summary. Thus, for all epsilon bigger than 0, there exists a trace of big N that, namely, big N equals 1 over epsilon. If you know what big N is, you may as well write it down. So that for all little n in n, if little n is bigger than big N, then absolute value of xn minus 0 is less than epsilon. Oh, and I guess that's also the content of that next sentence. So I don't need that now. How do people feel about that? That seem pretty okay? So if you want to prove a sequence converges to a number, start by considering any epsilon bigger than 0. Then do something to come up with a choice of big N. Maybe it'll involve doing some like algebra off to the side. Right, so that I would never want to see in your final write-up. I don't care about that. I care about your actual write-up. Do some stuff to come up with a choice of big N. Maybe it's doing some algebra. Maybe you know some things about the sequence. And those things about the sequence give you choices of big N. Do them. So come up with a choice of big N. Then consider any natural number n. Assume that little n is bigger than big N. And then do something. Do this step, which will depend on what your sequence is. Yeah.
The very last line there is that it's supposed to be an absolute value at the end of epsilon.
Nope. Right, only xn minus 0 is supposed to be inside of absolute value. How do people feel? Does that seem okay? So let's do some more stuff. Does every sequence always converge?
No.
No. Here's an example. Well, definition. If xn does not converge to absolutely any real number, so if there does not exist a limit to a sequence, we say that it diverges. If there does not exist a number n such that xn converges to L, we say xn diverges. And here's the prototypical example. Well, I don't know. Like you said, not every sequence converges. What example were you thinking of?
I think it was 1 over x. And no,
good example of a function that fails to converge at a particular input. That's a definition that we'll hit later on in the class. What seems like an example of a sequence that maybe doesn't get close to a single number? So I just need some rule that takes a natural number, gives me a number. Those numbers don't get close to it. And yeah.
Maybe like x squared.
X squared. So is x the natural number? No, you're good. I just want to, like, is x the n?
Yes.
Yeah. Okay, so n squared. As n gets big, what can you tell me about n squared? It will be being very informal.
It keeps growing.
It keeps going. It gets big. So if it keeps getting big, it's not getting close to a single input. There's a thing that diverges. That one diverges in a particular way. Like, it's not getting close to a number because it's trying to get close to infinity. So we'll mention that definition soon. Here's the example that I want to actually talk about right now. -1 to the n. So that's the sequence that the n equals 1, it's -1, then it's +1, then it's -1, +1. Does that seem to be getting close to a single output? No. It's like bouncing between two. So there's an example of a thing that does not converge. Shall we prove that that thing diverges? Yeah. So let us prove that this does not converge. So if you think about what you would need to prove, you would need to prove that there is no choice of L that you could put here. So something like there does not exist a choice of L such that this stuff happens. So that seems like it would be a pain to negate. So maybe I'll go with this. Let's assume it does converge to a number L and then get a contradiction. Let's try to do that. So let's suppose that this thing does have a limit. Let's call the limit L. And maybe we'll see what sort of contradiction we'll get. So if you want to plot the sequence, we do something like that. And let's suppose this was the limit. So that limit has to be really close to 1, probably, and also really close to -1. Is there anything that's really close to both +1 and -1?
Like equally close to the two?
No, really, really close. Simultaneously, really, really close. Is there anything that's within 1/1,000,000,000 of 1 and 1/1,000,000,000 of -1? No. So that's how we're going to get our contradiction. We'll show that this L has to be really, really close to 1 and has to be really, really close to -1. So, cool. So let's parse this out. So we know that this thing has a limit. We'll call the limit L. This means that for every epsilon, there is a choice of big N, which depends on epsilon. Sometimes I'll use this notation when I want to encode the dependence of N on epsilon.